Okay, good afternoon folks. Thanks for coming along. My name's Thorn. This is my partner Alex Stuchbery. I'm entering fourth year of a mechanical engineering degree at RMIT in Melbourne. Alex is entering third year of a double degree at ANU here in Canberra in science and mechatronics engineering. I'd just like to say a quick thank you to Northrop Grumman for funding the AITC student internship program. Thank you for giving me a bed to sleep in. Today we're going to be discussing vibration measurements of the EOS guidestar laser unit and its proposed location within the 1.8 meter telescope dome up on the here at Mount Stromlo. We're also going to be talking about thermal measurements of two of the Coudé mirrors and their mounts. So just a bit of quick background with respect to Stuchbery adaptive optics and how it relates to our project. Space debris is becoming an increasingly serious issue. Tracking debris currently is not very accurate, and due to this inaccuracy, satellite operators tend to ignore warnings from tracking stations and, well, how did you put it?
They take the close their eyes and pray approach.
Yeah, so eventually another collision like the one between Iridium and Cosmos, given enough time, probably happen. So not a good situation. The adaptive optics program here at the EOS laser tracking station is endeavoring to increase the tracking of space debris. And for an adaptive optics system to work, you need a guidestar. And that tells us what effect the atmosphere is having upon the wavefront of incoming light and what we need to do to correct that atmospheric effect and produce a better image. When you're tracking a high velocity object across the sky, like a piece of space debris, natural stars aren't quick enough to keep up. So we need to create a fake star in the upper atmosphere using a guidestar laser. And the one currently under development by EOS is highly sensitive to vibration. Measurement of that vibration is one of the main focuses of our talk today. So I'm going to pass you over to Alex to talk about that.
Thanks, Alex. All right, so if we have a quick look at the final laser design, sorry, wrong laser. The final EOS laser design, you can see here's the telescope picture which you've seen before. Now this telescope is going to output vibrations, and those vibrations are going to go into the laser bench, which you can see here. And on this bench, it's then going to do something to the vibrations, we don't know what, and then input them into the laser itself. So on this block diagram down here, in green is what we've done as part of our project. So we've measured the output vibrations of the telescope, and we've measured what the laser unit can stand as an input before it fails. We haven't looked at the laser bench itself because it doesn't exist yet. It's still under design and development, and the measurements we've made are going to feed into the design of that bench. So to measure vibrations, we used a sensitive 3-axis accelerometer. The details are up there. Now we had to calibrate this, and both the accelerometer and the calibration exciter haven't been properly calibrated for several years, and it's really expensive to do it. So when we stuck the accelerometer on the calibration exciter, we measured exactly what we were supposed to at the exact right frequency. So if either of them have drifted off calibration, they will have had to have drifted by the exact same amount in the exact same direction. Since that's really small chance of happening, we decided the calibration was good enough and plowed onto some experiments. So in the optics lab where they're building the telescope, we strapped the accelerometer here as close as we could to this optical cavity. Now the reason we did that is this optical cavity is the most sensitive component on that bench to vibration. We'll come back to that in a second. Then we connected the accelerometer up to a Sirius box fed into a laptop running DeweySoftX software, and that whole system kind of works as our data acquisition system. Now this optical cavity, it needs to be sized to within a fraction of the laser's wavelength for the laser to work. And in the case of this laser, that's a fraction of a micron, so you don't have much wiggle room. To keep it at this exact distance, piezo actuators controlled by PID controllers were attached to the optical cavity, which compensate for vibrations. When they're not working perfectly, light escapes in an undesirable way from this cavity, and we can detect that with a photodiode. This photodiode's output was plugged into our data acquisition system, so we could get the deterioration of the laser by way of this escaping light time correlated with the vibrations. What you can see here are a few time series of tests we did. On the top, we've got our vibrations in the X, Y, Z axes, which were just X, Y, Z in the laser room. And on the bottom, we have the output of a photodiode. So the higher these peaks are, the more the laser is deteriorating. So we kept tapping on the bench until the PID controllers could no longer compensate for the vibrations and the laser stopped working, which is what you see over here. What we could determine from this test is a vibration over all frequencies at this point of 0.025 meters per second squared, note that gravity is roughly 10, is enough to degrade the laser's performance with these little bits here. If you go an order of magnitude bigger than that, to 0.25 meters per second squared, it stops the laser working in this big tap. What was really interesting is in a different test, which is on the bottom, it wasn't a singular big tap, but a series of really fast, quick taps, which were smaller in magnitude, which caused the laser to fail. So note the time scale on these two tests are different. So this series here occurred faster than any series of taps in the top test. So we're going to look at the frequency spectra of a few of these taps next, specifically this big one, which caused the laser to fail, and this smaller one, which didn't. So here, by analysing the difference between these two, we can try and pinpoint exactly what caused the laser to fail. So straight away, there's a peak at 101.2 Hertz in both cases of roughly the same magnitude. So we can say that didn't cause the laser to fail because it was there when the laser was working just fine. However, the height and breadth of these peaks, this section here and this section here, all contain less energy. So we worked out how much acceleration there was over the whole 0 to 150 Hertz, and also in the band between 50 Hertz and 60 Hertz, which is this big peak. Why we picked that peak will become more apparent when we look at the telescope dome. But in both cases, the tap that caused the laser to fail was about twice as big as the tap that didn't. So a few other points that we noticed in the laser room before we move on to the telescope. Looking at the spectra of the single tap which stopped the laser and the multiple taps, you can see they've got roughly the same magnitude peaks at the same frequencies. So whilst they're different physical phenomenon, they induce the same vibrational response, which is why they both caused failure. The reason this one is a lot more narrower peaks and this one is broader peaks has to do with the maths behind the time we took the Fourier transform over. Another noticeable thing was that pressure waves from sound in the lab actually caused reasonably large magnitude vibrations in the laser. This isn't so much of a problem because they're all high frequencies, which the laser mechanical components don't see as much, and also you can damp out acoustic noise with soundproofing tiles on the final bench relatively cheaply. The three chillers that are used to cool the laser, we looked at all of them, and one of them, the make and model here, caused a large peak at exactly 50 Hertz and then smaller peaks every 50 Hertz after that. We believe that this is due to electronic noise, given Australia's mains frequency is 50 Hertz. So moving on to the telescope dome, this part of the telescope right here is where they're going to strap the bench. This is just looking from the other side of the picture you saw earlier. So that's where we put our accelerometer. So the telescope rotates in azimuth around the Z-axis, and it goes in elevation from the X up to the Z, only 90 degrees. If you want to go over the other side, you've got to turn the whole thing around 180 in azimuth. So the telescope baseline spectrum was taken with absolutely no movement of the telescope and none of the instruments working at all. This dotted red line is the top of the spectra on the tap that caused the laser to fail. So straight away you can see we've got a couple of peaks that are going way above it, and this 56 Hertz peak is the exact same peak that was the one we looked at earlier in the tap which caused the laser to fail. Now, these are narrow peaks, whereas the others were broad, so we looked at how much vibration was contained within these peaks up here, and this is just a reminder of what the old numbers were, and it's just above. So with absolutely nothing happening in the telescope, there's just a bit more vibration there than what the laser could handle in its present state. If we now look at the telescope tracking a fast-moving object across the sky, we're an order of magnitude worse in vibration. So this dotted line now is the maximum of the spectra I just showed you one slide ago. So you've got multiple peaks going much, much higher. All the magnitudes of vibration are an order of magnitude higher. We've also introduced these high magnitude, low frequency peaks, which weren't there before. This is probably due to the telescope constantly accelerating and decelerating in its motions, tracking an object, but these are going to have to be addressed, seeing as tracking is exactly what we want this whole system for. So, and that, again, just a few quick points that we noticed in the dome as well. The instruments, which are along this truss here, have to cool, and their cooling systems are just as disruptive as moving the telescope itself. So once they're finished cooling, the vibration dies down below what we can detect in the baseline spectra. So we recommend that all the cooling be done first for all the instruments to be used, and then the laser gets turned on to avoid those two interfering with each other. And finally, the X direction, which you can remind yourself is across this way, has a lot more high frequency vibrations in it than the other two axes. We haven't had a chance to look into why that is, other than just to say if there is a component which is sensitive to high frequency vibrations, don't align it on the X-axis because it's by far the worst. I'm going to pass you back to Elliot now to talk about some of the work we did on the Coudé mirrors.
Okay. Okay, so the Coudé mirrors and their mounts pictured here are critical components in the telescope's optical parts. The two under consideration for our project require realignment every 2 to 3 months, and it's suspected this may be due to temperature changes inducing thermal deformations in the mounts, and this can then have the effect of changing the light path angle of reflection, and this can then go on to degrade general telescope performance. So this has been an ongoing investigation by EOS, and to supplement that investigation, we attached temperature sensors to Coudé mirrors 4 and 5, pictured here. You can see their location with respect to the rest of the telescope structure. The objective of that was to measure the maximum and minimum temperature components, find the lag time between the maximum external air temperature and maximum internal ambient air temperature, and to fit the K-curve to the measured data to figure out which component cools the fastest. So we attached sensors to the same spots on both mirrors. We've suspended one behind the mirror in between these angle brackets, and that's to measure the ambient air. Then we've attached 3 more to the mirror mount base plate, the mirror mount rear flexure, and the side of the mirror itself. We carried out a 2-point calibration procedure using ice water and boiling water to generate mean temperature offsets. You can then apply those to the measured data to yield relatively accurate temperature values. These are the sensors that we used. So you can see here that the errors are quite small. They're more than accurate for the purpose we required them for. Okay, there's quite a lot going on in this graph, but I'll just point you to a couple of things. We've got the maximum, the external ambient air temperature here on the blue curve, and the maximum temperature component is the mirror 4 mount base plate. That's the black dotted line at the top. And the minimum recorded temperature was in the mirror 5 ambient air, and that's the solid red line at the bottom. We found the average temperature difference between the upper mirror and the lower mirror to be 2.2 degrees C, which seems like a lot considering that the height difference is only 1.9 meters. So a possible explanation for that is that the steel grated floor that runs around the dome, it actually cuts in between here, so you walk along there, separating the two mirrors. That might be acting as a kind of passive diffuse thermal barrier. Another possible explanation, when we were setting up the sensors on mirror 5, we noticed air flowing over it. So mirror 5 and its components may be benefiting from some kind of convective cooling effect. On the left here, we've got an example of the lag time. The blue curve is the external ambient air, the red curve is the mirror 5 ambient air, and the difference between the peaks is the lag time. These are the lag times that we found here. On the right, we've got a decay curve fitted against the measured data. We did that using Newton's law of cooling. We had a MATLAB script that iterated through the decay rate constant K to find the temperature of a component at the time T. We then used a sum of squares function to determine which value of K provided the curve of best fit. And after all that was done, the results were that the mirror 5 base plate cooled the slowest, and the mirror 5 rear flexure cooled the fastest. So it's not that surprising considering that the base plate's made of steel, the flexure's made of aluminium, and aluminium has a thermal conductivity approximately 4 times higher than that of steel. So it's able to conduct heat into components that are adjacent to it and in contact with it at a much higher rate. Okay, so to wrap all that up, we detected possibly problematic vibration between 0 and 150 Hertz. The telescope baseline vibration may impair laser functionality. We'd recommend that soundproofing tiles be affixed to the laser enclosure in order to damp any disturbing acoustic inputs. And we'd also recommend that all the instrumentation is allowed to sufficiently cool before the lasers are activated. And all of the thermal data is going to be passed on to EOS to aid in their continuing investigation. So thanks very much. We'd just like to make some acknowledgements, and that's it.
Yeah, so.
Any questions?
Yeah, guys, did you consider using an active vibration damping interface between the laser cavity and its mounting structure?
We're not designing the laser. That would be something to put over to EOS. Yeah.
Okay. Also, what were the sources for these high spikes that you were seeing in the vibration spectrum? Did you ascertain what they were?
Which particular, the low frequency spikes in
Yes.
the tracking?
Yeah.
Look, we theorized that it's because in the tracking test, it's the only test where the telescope is accelerating and decelerating constantly, whereas all the other motions, it sort of accelerates up to speed quickly and then stays at a constant speed. So that's what we believe it to be, because that's the only thing we could think of that was unique to that test. But if you really wanted to pin it down, you'd have to do a few more experiments.
Right. Okay.
Any other questions?
It says
Yep.
the laser phase when you continuously tap rather than repeatedly tap.
Yes.
Did you try different combinations of PID, parameters of PID?
No, we didn't, because our main aim was to look and see what the telescope was doing. Also, the laser is still under development, so it might change, but that's definitely what future research should be put into, because yeah, you get both in the dome. You get sudden jolts when it starts moving, and you also get continuous periodic things from cooling fans and whatnot. So yeah, that does need to be looked into. Yes, Craig.
Can I just say thanks, guys, for the work done. You don't often get the opportunity to do that sort of in-depth analysis, so the time you spend on it is appreciated. Certainly what we've seen is that we're going to have to raise the bar on the vibration resistance of the laser, and that's exactly the task that we set you, that we wanted to know what is the threshold at which we have to be able to resist a vibration. We've done exactly that, so I think it's a great job.
Thank you very much.
Thanks, Craig.
Thank you. It's been a pleasure.